Good morning, class. Today we are going to discuss crystal imperfections as a part 3 of our first unit in metallurgy and material sciences. So, let's first understand what is crystal imperfections. So, the idea of perfectly regular crystal structures in which atoms are arranged in a regular way does not exist. So it means that if you take any kind of material, whatever it may be, either it is a gold, either it is a silver, or it is steel, so any kind of crystal structure, the atoms will not be arranged regularly. So there will be few flaws in it. So all the atoms will not have the perfectly regular crystal structure. Okay, if you take any item, any kind of material, so it is purely an ideal nature of material to have a regular crystal structure. So in actual case, the regular arrangement of atoms will be, obviously it will be disrupted. So these disruptions are called as crystal imperfections or crystal defects. For example, if you take as a human being, no human being is a perfect. No one is an 100% correct. So there are every human being will have some flaws. So similarly, a material, a complete crystal structure material is completely an ideal nature of a material. So there will be some imperfections. So any kind of deviation from the perfect crystal, we generally call it as imperfections. Okay. So the if you take crystal imperfections, that is nothing but an not perfect, not properly arranged materials. So with this, what generally the scientists do is they can able to create the new materials with the help of these small imperfections. So if there are some, for example, if a student is not good in a class, so teacher will try to give some extra notes to him so that he can become he can write the exam properly. So similar way, if material is not perfect, so what scientists will do is he will try to add some of the features which are missing in it so that we can create an perfect crystal. So example you can take, you can, if you have steel, so steels are of different types. So stainless steel, for example, steel is having a drawback of getting rusted. So that is formation of Fe2O3. So to avoid that, what scientists have done is they have added a small amount of chromium to it. With the addition of chromium, this chromium will react with the oxygen and forms a layer, so which will avoid further formation of Fe2O3. So with this we can avoid the rusting of steel. So this is the main advantage of chromium adding to a crystal structure of steel. So with this only we have found a new material, that is stainless steel, which you are daily using in your home activities. Okay. So why do we care about these defects? What is the importance of these defects is, so crystal imperfections have strong influence upon the properties. So it will purely influence the properties of materials such as strength, electrical conductivity, hysteresis losses. For example, if you have studied in lower classes like 10th, 12th, you might have studied about semiconductors. In semiconductors, there will be like arsenic, germanium, in which we dope some materials with the help of which they can able to conduct the electricity. Okay, with that we can able to study about the forward biasing, reverse biasing of semiconductors. Similarly, with the addition of few materials, we can improve the strength of material, conductivity of material, and we can reduce the few losses in it. Okay, that is the importance of this crystal imperfections or crystal defects. Okay, so these are the few things. So the conductivity of semiconductors is due to entirely the traces of amount of chemical impurities. What are the impurities you are going to add? And few materials like plastic, if you see in the plastic, we can add some colors to it. So by adding few what we say imperfections, we can create the color in a plastic. Atomic diffusion may be accelerated. So if there are few large amount of holes, we can able to add more amount of atoms to it. Okay, so the chemical properties and plastic properties are generally controlled by these imperfections. The most important feature of the microstructure of an engineering materials are crystalline defects. So this is the one of the most important topic in whole metallurgy. Metallurgy is nothing but study of materials. So in this is the one of the important topic, how the material is going to have the crystal imperfections. Why we say this is the important topic is, until unless you know some of the defects of a material, you will not understand how to improve the nature of that material. For example, I have told an example of steel. So until unless we know that steel gets rusted when it combines with oxygen, we cannot able to overcome that defect. So again you can take an example of a student. Until we know the flaw of a student, why the student is going to fail in some subject, until then we cannot able to help him. So same way, until unless you understand the material nature, why the problem is generally happening, so if you understand that problem, we can able to rectify that problem. And why that problem is coming is the main reason of that problem is because of the crystal defects. Okay, so there are various defects, okay, that we are going to see. So first of all, they have divided the categories of the crystal defects into 4. The first one is zero dimensional defect, or we even call it as a point defect. So which occurs exactly at a single lattice point. What is a lattice point? It is an infinite number of points on a space. So next is line defect or one dimensional. Line is a one dimensional. Okay, it is also called as dislocation. Dislocation means completely it is dislocated. For example, if you go to a doctor with your broken arm, he will say your bone is dislocated. Actual location of the bone is being displaced. Similarly, if there are atoms in a certain crystal line, so that complete line will be displaced from its original position. That is called as line defect. Next is surface defect or two-dimensional defect. So in this surface defect or two-dimensional defect occurs on the whole surface. These all defects generally we study under microscopes like scanning electron microscope, tunneling electron microscope. So these are optical microscopes. So surface natures can be studied by optical microscope to till some extent. Okay, each and every microscope will have some range. So to what micrometers we can study using that. So if you want to still go deeper, they have to use a huge microscopes. Okay. So next is volume voids. So volume voids is nothing but the whole element will be missing. For example, we have studied a 3D unit cell where the n number of unit cells are combined together to form one crystal. So one complete unit cell or complete 2 to 3 unit cells will be missing. So that kind of defects are called as volume defects. So again I am repeating, point defect is a particular atom at some lattice point. So line defect is nothing but one dimensional where the line is being displaced from its original position. Surface means the plane on which the atoms are existing. For example, if you can say BCC, FCC, there are some elements, atoms existing on the face of the element, that element may be displaced from that face. So that kind of defects are called as surface defects. Next is volume defect. Volume defect, a unit cell, whole unit cell can be displaced. So we are still going to see further how it is going to be, what are the various types again in point defects, line defects, surface defects, what are the subdivisions of this we are going to see. So point defects, first of all, vacancy. Vacancy is nothing but if there is some atom missing, okay, then it is called as vacancy. Next is interstellar. So for example, there is some extra atom presenting in it, self atom. Next is substitutional impurity. If some atom is coming from outside and it is substituting the already existing atom. For example, you are sitting in your place, some person comes and makes you, he replaces you from your seat, then it is substitutional impurity. Next is Frankel defect and Schottky defect, which we will see further. Next is line defect is of two types, edge and screw. Surface is grain, tilt, twin and stacking. Okay, volume is inclusions and voids. Okay, so let us see what is a point defect. Point defects are when an atom is missing or an irregular place in the lattice structure. So for example, if you take this arrangement of atoms, in this a small atom is missing from the lattice space, so then it is called as vacancy. So in the same atom, what is happening is already every atom is filled in the lattice, one extra atom of same element is coming and sitting here. Okay, then it is called as interstitial. Next is if an impurity, other element other than, for example, if it is water molecule and in water molecule some other compound is coming and sitting, so this is called as an impurity. So the example of this impurity, you can take it as semiconductor. Generally in semiconductor, what happens, we add some impurities, doping will be done to the semiconductors. Okay, in ceramics this kind of effects will be seen, that is Frankel defect, Schottky defect. This is nothing but in Frankel defect what generally happens is an cation along with the cation interstitial pair. So both will be displaced, and the whole atom will have a neutral nature. Okay, the cation vacancy and the cation interstitial pair is known as Frankel defect. What does this mean is cation will be displaced from its position, whereas the another cation will be arranged instead of its own place, it will be arranged to a displaced position like as a interstitial. So this atom is displacing and it is going and sitting here. So with this, what is happening, because of this missing, this whole atom should have negative sign, even though what is happening, again another atom is coming and sitting here which is replacing this atom. So because of that, cation the anion nature will be lost from the material. Okay, cation vacancy and cation interstitial. So that is nothing but, actually this was the arrangement. In this arrangement, this atom should be sitting here. Instead of sitting in this position, what it is going and sitting here. So there is neutral. If you see as a whole, it will be a neutral nature, but if you see the place, the small gap is created. So this kind of defect is called as Frankel defect. Whereas in Trotsky defect, what is happening means a cation and anion both as a pair will be missing from the element. Okay, both cation and anion both together as a pair will be missing from the atom. Okay, so this is here when an ion is displaced from the regular side to another side. So the ion will be inside the atom itself, but instead of sitting in its own place, what it will do is it will go and sit in the other place. Okay, it will go and sit in other place. Cations are generally smaller ions. It is possible for them to get displaced in the void. Those will be in a small nature. Because of that, it can move in the atom. Okay, move in the element. To maintain the charge neutrality, cation vacancy, cation interstitial pair occurs together. So these two, because one atom is missing, again another atom is going and sitting in the other place. So if you see this, what will happen is the whole atom will come as a whole element will come as a neutral. Next is Trotsky defect. In this, when a pair of atom, cation and anion is missing from the lattice, okay, the defect is known as Trotsky defect. This is closely related to the vacancies. To maintain the neutrality, one cation and one anion, always two together, one cation and one anion will be missing. Next is line defect or dislocation. In this, we have studied, I have explained about two things. One is edge and another is screw. So this is edge type. So in this, what happens means the edge will try to move forward. So the dislocation is a region of localized lattice distortion. So if you are applying some shear stress, what will happen to the edge of the element is edge of the element will try to move forward. The upper region of the crystal will will move forward compared to that of the lower crystal. Okay, this is called as slip. Slip is nothing but the motion. The movement is called as slip. For example, if you are walking, if you slip, what happens means your front or any one of your leg is, instead of keeping at one position, it is moving forward. That is called as slip. Same as in this, the material instead of at the edge, the both edge should have been joined, or both the edge should be aligned to one another. Aligned means both should be on the same line. So whereas in this defect, what is happening is instead of they are on the same line, one edge is moving forward. Okay, because of shear stress. Okay, that is called as edge defect. And this edge defect is generally studied by using two vectors. One is used to explain the magnitude, another is used to explain the direction of the motion of the edge or slip. So in which direction you are going to slip. For example, you are moving forward. If you slip front, you will be moving. You will be falling backside. For example, if you are moving, if you are walking, if your left leg slips, then you will fall front. So similarly, we have to understand how the slip is going to be propagated, how it is going to happen. So that is studied by a vector called as slip vector, or we even call it as a Berger vector. Okay, we call it as a Berger vector, and the direction of motion will be always perpendicular to the edge. Edge will be perpendicular. Okay, so see this. So if you see this perpendicularity, so this is going to happen. Okay, so with this, what we can understand is one side of the atom will be under compression, another side of the atom will be in expansion. So if this is a slip happening here, So because as the atom will have this equal amount of space, for example, if four people are sitting on a bench, if some fifth person comes and tries to sit in the same bench, what will happen? It becomes congested to sit, so which will create a compression in between the students. So similarly, if say instead of sitting here, if the edge moves forward, it will create the compression between the whole atom which is above the slip, and these will be under tension. Okay, this will be under compression, this will be under tension. So because of this tension and compression, again the edge dislocation will be divided into two types, that is positive and negative. So the positive dislocation and negative dislocation. So the edge dislocation is considered to be positive when compression stress is present above the dislocation. If this is my dislocation and your compression is above, then it is called as a positive. If the compression is opposite, for example like this, so if the compression is in the lower part and your slip is on the above side, okay, then this kind of slip is called, the edge dislocation is called as negative edge dislocation. Okay, you can consider in other ways also. For example, if you consider this as a origin, so above the origin it is positive, so this is a positive dislocation. Below the origin there is a compression, that is why this is called as a negative dislocation. This is the shortcut we use generally say. Okay, so for example, see this was the arrangement of atoms, 1 to 1 is aligned, 2 to 2 aligned is aligned. So say equally it was aligned. So because of this forces, that is nothing but this forces, what will happen is, if you see, so the one will be displaced to somewhat. This is called a slip. It is happening slip. So after certain point, okay, after certain point, the slip will be will not be occur. So that is nothing but called as non-slip, no slip or non-slip. And this region is called as slipped region, this is called as non-slipped region, and the boundary is called as edge dislocation. This is the edge which is creating the dislocation. This edge is moved forward, because of that only this is created, and this whole plane will be called as slip plane, and this whole plane is called as slip plane. So this is the direction in which your slip is going to move. That is the reason we show as a Berger vector B, which is showing the direction of the slip. Okay, there will be another vector which will represent, so this is another vector, unit vector we generally call, so which shows the direction where slip is not happening. So beyond this there will not be slip. Okay, so this vector is nothing but a unit vector tangent to the dislocation line. So wherever the dislocation is happening, perpendicular to that we write a tangent, that is nothing but a unit vector tangent. Okay, so these three things you have to remember: dislocation line, Berger vector, and line vector or slip vector, which is nothing but a perpendicular to the Berger vector. Okay, in case of edge dislocation, whereas in for example again, okay, so again if you see this, so this is the same example where we are going to show the T, that is nothing but the tangential to the plane. Okay, so this is slip is perpendicular to the edge, whereas this is parallel to the edge. So both are perpendicular to each other. This is unit vector, this is my Berger vector. Okay, so how we are going to identify the Berger vector is, first of all you have to draw a Berger circuit. For example, take this atom. So first of all, when before the happening of the what we say dislocation, we have to draw a circle in clockwise direction. You have to understand in which edge or which place it is going to happen. So with that, what we have to draw is, we have to draw a circuit. This circuit is called as a Berger circuit. Once you complete the circuit, and after applying the shear stress, there will be some dislocation created. Now with the same what we say circuit, we are trying to close the atom or the element. So while closing, we will see that there will be a small gap left which is not able to fill. Now if you ask me, sir, how you have joined all these things, so see this is of length, you can consider from here to here what is 1 unit, 3 units. So here also 1 unit, 2 unit, 3 unit. Here also 1 unit, 2 unit, 3 unit. Here also 1 unit, 2 unit. So same arrows I am using. Only thing is missing is, while coming at this position, when dislocation is happened, I couldn't able to complete the circuit. So with that, I could able to understand how much length of dislocation has happened and in which direction the dislocation has happened. So first of all, we have to draw a Berger circuit for an element in which there is, so if you want to read this, an atom by an atomic circuit is drawn around the dislocation line, and the vector needed to close the circuit is known as Berger vector. In perfect crystal, there are no dislocation, and such circuit will be closed without any mismatch. So if there is a perfect crystal, obviously it will enclose completely. So when dislocation happens, there will be some missing gap. So like this. So that is again I am going to complete by drawing a line of on the direction. So with this I could able to understand the length of the Berger vector and the direction of the Berger vector. Okay, this is again the construction how it is going to happen. Next we are going to see is screw dislocation. In screw dislocation, what is happening is, instead previously I have seen that the edge is moving forward. In this case, instead of edge, so this side will try to move in this direction along the surface itself. So okay, this kind of dislocation is called as screw dislocation, and in this screw dislocation the Berger vector will be parallel to the surface, okay. If you want to take the relationship, so this is also okay, you can take an example of a sponge. If you are trying to push the sponge, only a certain part will be trying to move, other part will be at the stationary. Okay, clear? So the upper part of the crystal right of the AD has slipped relative to the lower part of and the direction of slip vector. In screw dislocation, the Berger vector is parallel to the dislocation line AD. That's what I told. Wherever the dislocation line is happening, to that line the Berger vector direction is parallel, whereas in previous the dislocation was happening in this direction and vector is moving in this direction and the edge is perpendicular to it. Okay, the traces of the atomic planes above the around the screw dislocation makes a spiral or helical path like a screw, hence the name is given. Atomic position along the screw dislocation is represented as this. So whenever the screw dislocation happens, there will be formation of spiral or helical path. Okay, spiral or helical path, you can observe this. Okay, at this position it will form a spiral or helical path of the atom. Because of that reason we call it as a screw dislocation. Okay, again in this, if you want to see, this is a slip plane and this is going to be slipped and this is non-slipped or unslipped area. Okay, and the direction is nothing but it is shown by using a Berger vector, to what length it is going to be slipped. Okay, so this is the direction how we take. If it is in right hand thumb rule and left hand thumb rule, it is the positive, it is negative. Okay, clear? So next is surface defects. Surface defects are also called as 2D defects in nature, and they occur due to the change of stacking of atomic particles. So when atoms are being arranged on a surface, if there is distortion, if there is some missing of atoms in a arrangement, for example, all students are sitting one after the other and some person and sitting in reverse direction, then it is called as a surface dislocation. He is trying to orient himself in wrong direction, because of that surface will be changed. So this is one of the example. When for example, if you are doing casting, so in casting what you will do, you will melt the metal and trying to cool it. So while cooling, what happens means some of the elements will try to arrange in different directions. So this will create a boundary among this is called as a grain boundary, and this kind of dislocation or this kind of defect is called as a surface defect. Okay, so one is grain boundary, another is tilt boundaries. Tilt boundaries is, instead of having a straight boundary, there will be tilt happening. So instead of in a sequel way, what they will go is, there will be a small deviation in each and every line instead of being in a parallel. So next is twin boundaries. A shear force that causes the atomic displacement such that the atom on one side of the plane mirror the atom on the other side. So they are in mirror nature, but they are in a, if you see this, so here it is 3, okay, here it will be 3, so that way it will be exactly twinned. Okay, exactly it will be twinned. They have not shown properly here. So twin boundaries occurs in a pair, resulting in a region of different orientations in a crystal. Twin boundaries formed during crystal growth. We will see about how the crystal is going to have a growth in its nature. So with this, there will be mechanical deformation, or there will be mechanical changes in the properties, and this we generally call as annealing. So annealing is nothing but cooling or quenching of a material by using some liquid, oil, or by air. Okay, so for example, this was the atoms arranged with this, they are going to be displaced. This was the actual path. If you see this, they are going to be displaced like this. Okay, and this is nothing but called as twin line and twin boundary. These two are called as twin boundary, and this is the twinning happening. Okay, clear? So next is stocking defect. What is stocking defect in generally is, stocking is nothing but arrangement in proper order. Stacking is nothing but arrangement or repetition. For example, ABC, ABC, ABC. Instead of in this, what will happen is sometimes it will be ABC, AB, ABC. So one atom is missing, C is missing here. So in this way, what the atoms will do is, instead of being cation, anion, sometimes it will do cation, anion. So in this way, the atom is going to be arranged, stack themselves in irregular manner. That kind of defect is called as stacking defect. Okay, the role of surface defect in crack initiation. How this surface defects will help in crack initiation is, the atoms located near the grain boundaries. I have already told you what is a grain boundary. The boundary drawn between the arrangement of atoms is nothing but called as grain boundary. Have distorted and non-equilibrium surrounding at high energy level. These boundaries at some points will have high energy level. For example, some boundaries can be easily breakable and some boundaries are not easily breakable. So every atom at an exterior surface have some same situation. If you see from the outside, all will see look at a same. So the exterior surface is usually rough and contains tiny notches. Notches means if you take any kind of material, no material will be 100% smooth. There will be some small surface roughnesses on the material, that is nothing but small notches will be existing. So this will create what is this notches will be able to initiate the crack. That is the reason we try to make the material as smooth as possible, but if you make 100% smooth, then holding of that atom will be not possible, and with this notches itself the crack will be initiated. For example, if you have your mobile, so in your mobile, if once a small crack initiates on your tempered glass, so that crack will be propagated and it will distribute on your whole tempered glass. So that is nothing but how the crack is going to initiate and propagate is because of the grain boundaries. So whichever the boundary is easily breakable, the crack will try to move in that direction and it will try to crack the atom or the element. Next is volume defects. Volume or bulk defects. Voids, inclusions, etc. present in a crystal are called as volume defects. So void is a large vacancy. We cannot say small voids, we have to be a large vacancy. That is nothing but cluster of atoms. That's why I was told one complete unit cell or 2 to 3 unit cells should be missing from an atom, then it is called as a volume defects. Okay. Next, voids due to air bubbles. Generally in casting, what we see is, for example, when we are doing casting, the molten metal, when it is poured into the mold, there will be small air gaps produced. Because of that reason, we try to remove the air bubbles. Okay, this air bubbles will create a porosity in the atoms or porosity in the elements. Okay, the voids due to shrinkage of material, again those are called as cavitations, and inclusion of other materials. For example, these are all generally seen in casting itself. When you are doing casting, there are some other impurities like dust, like mud can even pass through the casted material and it will create a cracking of the material. Okay. Next is precipitates. Precipitates are certain regions within the crystal which are occupied by the other phases. For example, if you take water vapor, in water vapor there will be small water droplets. Those we can call as precipitates. Okay. So next up, sources of dislocation. What are the various sources of dislocation is, large number of dislocations existing at the same point will help you in formation of plastic deformation. So that is the reason in general in sheet metal work we try to create the material bending by hitting at a same point, because if you keep on hitting at the same point, all the dislocations will be created at the same position, which will help you in the formation of plastic deformation. Even in basic crystals there are some imperfections including dislocation orientations originates from various sources. The primary source is natural consequences of crystal formation. Natural consequences is nothing but when the atoms are going to be, for example, if you take water, you are trying to cool water to form an ice. So because of some if water is having some sand particles into it, when it is going to form an ice, that sand particle will be inside the ice itself. So that will create a small disturbance in the whole atom. Okay, some sources of dislocation can be vacancies, cross slip mechanisms, or high angle grain boundaries. Another source of dislocation is itself, and it is observed that during plastic deformation the dislocation density of the crystal increases by 2 to 6 times whatever the crystal dislocation was existing at the initial stage. That's why I told, if you want to bend the material in a sheet metal, we generally try to hit the material at the same position so that the dislocations can happen at the same point. It will create the plastic deformation to the material. So first of all, what we have to understand from all of these things is, to do a plastic deformation for any kind of material, dislocation is important. If there is no dislocation, then the material cannot be able to undergo plastic deformation. Sir, can you tell me an example? Means I can give an example of glass. If you take a glass, there is no plastic deformation, because in plastic deformation there will be no dislocation. It will die. The dislocations, if once the dislocation creates, I have given an example of tempered glass. If once dislocation is created, it will try to break the whole glass within short duration of time, because the crack initiation will be easy, since there are less number of weak grain boundaries in a glass material.